We'll start quantum mechanics with a property of particles called spin. For now, do not think of it as an arrow or a little spinning particle or whatever. Just think of it as a simple, intrinsic property of an electron that points in some direction in space. Okay, imagine a particle surrounded by an apparatus that can measure its spin. Something like this. If we can measure the spin of the particle along the up direction, that is, if we orient the apparatus along the z direction, the positive z direction, and measure the particle's vertical spin, we initially get a value of sigma, our symbol for the measurement, and it equals positive 1. Let's measure it again along the z direction. It's still positive 1. So far, so good. What if we flip the apparatus by 180 degrees to measure the spin in the down direction? Something like this. When we measure this, the apparatus spits out an answer of sigma equals negative 1. Which makes sense. The spin is pointing in the opposite direction of the apparatus. Here it's pointing up, so the apparatus is pointing up. Here it's pointing up, the apparatus is pointing down. So the answer is negative 1. As such, direction in this case affects our measurements. The apparatus's direction can change what the measurement is. Now let's try something different. Suppose we orient the apparatus along the x-axis, pointing right, like this. Classical mechanics would tell us that since all of the spin is pointing up, this direction, we would get an answer of 0 for sigma, right? Wrong. When we measure sigma, it turns out to be plus 1. How is this even possible? But it gets stranger. Suppose we repeat the experiment. Measuring the spin in the up direction first, getting a sigma value of plus 1, and then measuring it along the right direction. This time, we get minus 1. Repeat, minus 1. Repeat, plus 1. Minus, plus, minus, etc. After many runs, no pattern appears between the two outcomes. It just keeps going back and forth randomly. And we have no way to predict it. However, they happen equally as often. As we keep going, we can see that plus 1 is spit out 50% of the time, and negative 1 is spit out 50% of the time. It seems as though there's an equal probability for the experiment to measure sigma as plus 1 or minus 1 along the x-axis every time, but no way to actually determine which will happen. What if we do the first measurement in an arbitrary direction, such as this one, and then shift the apparatus to another arbitrary direction for the second measurement, like this? When we use statistical data for each situation, we find that the statistical average for sigma, shown like this. So the overall average of the value for sigma, in every case, no matter what the starting and ending points are, is equal to the dot product of the first measurement direction, n, the vector that represents this direction in space. The dot product with m, the ending position, this direction in space. When you take the dot product of these two vectors, every time you get a statistical average of the spin value. Now, we can clearly see that quantum mechanics is not deterministic. These experiments have been carried out countless times and consistently show that just because a particle is in one quantum state, that doesn't determine its other future states when measured. In fact, we can't even use standard sets of objects. We can't say the particle has spin up and not spin left. Those classifications have no meaning. So to truly master quantum mechanics, one must throw these assumptions out the window. In the next episode, we'll take a look at the math behind this field with ket vectors. Bye.